Thank you so much, and I'm very honored to be asked to speak in this company, and very appreciative of all the hospitality you've shown us. So some of the things that I wanted to talk about today have actually been very well covered by Frederick and also by other speakers this morning, so I'm gonna shift a little bit the focus of some parts of my talk. But I wanted to begin with just a little bit of a review of what we mean by the difference between AI and especially deep learning versus conventional computing of the kind that has dominated for the past 70 years, since the Second World War. So this is just a little random snippet of a program. What the program does is not important, but I put it up to illustrate the way computers normally work. You know, you as a programmer, you write a series of instructions. The computer follows the instructions. Everything is traceable and understandable, and the behavior of the computer is sequential and deterministic. And by contrast, I want to, hard rules written by an engineer, run by a machine, can contain errors and edge cases and unstated assumptions, of course, but it's generally straightforward to debug, because you can sort of step through it. Although obviously if there are millions or billions of lines of code, as unfortunately there are in many modern systems, then sometimes that explainability or that understandability can be quite illusory. All right, so now when we do a lot of the kinds of things that we've done with computers in the last 70 years, they really play to human weaknesses. We're very poor at counting. We're very poor at calculating trajectories of objects, unless it's maybe a ball thrown at us or something. So a lot of the traditional uses of computers in this kind of sequential mode complement human skills in a lot of ways. And by contrast, a lot of the things that humans and other animals with brains do very naturally and easily, like recognize objects, have been completely out of reach for computers for a very long time. So this is a very simple example. I assume everybody knows what we're looking at. It's not a trick question. It's a bicycle. You might think it's easy to write down a set of rules that will tell you why this is a bicycle. It's got two wheels, it has a handlebars, it has pedals, it has a chain. But you know, why is this thing not a bicycle? Well, it doesn't have two wheels, it doesn't have handlebars, it doesn't have a chain, it doesn't have a seat that you sit on. Okay, what if we put training wheels on the bicycle? Now it has four wheels. No, it's still a bicycle as long as there are two wheels in a row. What if I attach a trailer to it that I can pull a kid along it? Still a bicycle, nobody is confused. What if we attach a motor? No, then it's a motorcycle, not a bicycle. Unless the motor is not too big, then it's an electric bike. Or what if it's a tandem bike that no longer has just one set of pedals or one seat? You can see that the cases start to become very complex. And when you start to try to write down a set of rules that will determine whether what you're looking at is a bike or not, it's actually not very simple. We can look at something like this and recognize that even that is a bike. This is a little training bike for kids. Or you can look at these kinds of objects, and you know, we all kind of smile or laugh a little bit when we look at these things, because the whole point of humor is that it involves a violation of our expectations in one way or another. And nonetheless, we recognize that they're all bicycles, even though they violate every possible rule that we might have written down in our program that says, is something a bicycle or not a bicycle? These are the kinds of tasks that deep learning in particular can solve really for the first time. And the fact that it can solve them, that it can recognize bicycles like these, is I think probably related to the fact that these artificial neural nets look quite a lot like biological neural nets. I mean, we can argue about the details of whether they represent real neurons accurately or not. They don't. But I think it's not a coincidence that the moment when we started to really get these things to solve natural perception problems and motor problems and so on was also the moment when we got systems that have the same rough kind of architecture that brains have. This is my gesture. Yes. Okay, so I don't know if any of you have seen this 1958 movie called The Lovers. It actually caused quite a stir when it came out because it was a French movie, and I guess it was a little bit too sexy for the Americans. And it led to a US Supreme Court case as to whether it was pornography or not. That was Jacobellis versus the US, and Justice Potter Stewart, in his 1964 judgment, was the first one, as far as I know, to say of pornography, I can't write down why, but I know it when I see it. And in this case, it wasn't pornography. So this is a case of a legal expert who, of course, legal experts specialize in trying to make every decision explainable and trying to write down the procedure by which they arrive at a judgment, finally throwing up his hands and saying, you know, I can't do it. It's not possible, but I know it when I see it. And in fact, deep neural nets are exactly the right way to recognize porn. That's why when you do searches on Google, unless they're obviously pornographic searches, you don't get pornographic results, despite the fact that the majority of the internet is pornography. And that's because there are deep neural nets that are doing an extremely good job of filtering, for example, images, to make sure that those results don't show up in a non-explicit search. And those are things that could not have been done with conventional sort of rule-based programs. So AI is the study and the practice of knowing it when you see it, or hear it, or whatnot. Neural nets are very old. They aren't a new invention of the past few years. This is the first one, or the first one that is widely acknowledged anyway. Frank Rosenblatt, 1959. You can see what an artificial neural net looked like in 1959. It was a mess of wires. It was very difficult to engineer. But this neural net, this perceptron, was able to distinguish between triangle, circle, and square. So that was the first little bit of deep learning. It didn't go very far after this for quite a while, for reasons that might be obvious. For one thing, distinguishing between triangles and circles and squares is not all that interesting. The techniques for actually training such networks had not been developed at this point, so they had the values of the synapses had to be hand-coded, essentially. Or literally wired in by hand. But in principle, the neural nets that we have nowadays for visual perception, for example, are not really very different from this perceptron of Frank Rosenblatt in 1959. They consist of a sequence of artificial neurons. Each of them takes inputs from the previous layer, sums them up, applies a nonlinearity, passes that to the next layer. And that input layer could be an artificial retina that is looking at an image. The output could be the name of whatever it is that the thing is seeing, like cat or bicycle. And during the training process, which is the way these things are the way the weights are normally set, one has a set of ground truth data or training data, and there's a procedure for continually adjusting the weights of all of the synapses until the answers correspond to whatever the training data was. So you put in whatever, what you get out is a function of what you put in with respect to the training data. And Frederick has told us about some of the perils of the training data, either not being representative or having systematic biases or flaws. We heard also this morning about some of those problems. So once the data are trained, you can test it. It's generally a good idea to test a neural net or any sort of model with a different set of data than what is used to train it. And the reason, of course, is the same as the one that leads teachers to give students exams that they haven't seen before. If you give the student the exam at the beginning of the course, then regardless of what you try and teach the student, their most efficient strategy for scoring 100% of the exam is to memorize the answers to the questions. And learning is not memorization. This is a very fundamental idea. Learning is about generalization, meaning that you go from a series of examples to a general principle that allows you to answer the questions correctly, whether or not you have seen them before, if they're in the same domain. And that's why no machine learning technique is any good unless it can be shown to work on data that wasn't the data that it was trained with. So that's the 5-minute review of deep learning. If you're trying to recognize bicycles and you've never shown your bicycle detector a recumbent bike, then it's unlikely to recognize that this thing is a recumbent bike. That's of course true of people as well. We might do a double take or not know until somebody tells us, oh no, that's also a bike, and then we know how to expand our category to include this. And that's one of many sources of potential confounds that lead to violations of fairness. This is the simplest kind, as we've heard. This is the case where training data is just incomplete. We've just recently built the recognizer for faces that powers Pixel's face unlock feature that is shipping in the fall. And in order to ensure that this worked with all different kinds of faces, it was necessary to do a lot of the kinds of things that we have just heard about, making sure that the training data was complete, gathered faces of all different sorts, that we sliced up the training and testing data both in various ways in order to ensure that the performance was high on all different classes of people. That's not trivial for a variety of reasons, some of them having to do with even potentially biases built into the very nature of cameras and photography, and the fact that, for example, dark skin reflects less light. There are historical interesting examples from Kodak and the color film processes of cultural biases in effect being embedded in the very chemistry of photographic reproduction. So faces are a sort of a famous example of a way that things can go wrong with machine learning and bias. If it doesn't unlock easily for you, if your phone doesn't unlock easily for you, that's maybe not such a big deal. But this Israeli company, Faceception, is, I think, a much bigger deal. This is a company that it shocks me to learn is still around. I've used them a few times in talks that I've given, and every time I actually look up the website to see if they still exist, and they still do. This company claims that based on nothing but an image of the face, they can tell if you have high IQ, or an academic researcher, or a professional poker player, or a terrorist. And most alarmingly, their customers include departments of Homeland Security. So that tells us that something is going wrong. Obviously, these are some of the kinds of applications of AI and of machine learning that Google has committed not only not to do, but not to enable by proxy. It violates any number of our principles. And this really illustrates the way, when we talk about automated decisions and automated judgments, the results can be extremely consequential, and they can, as multiple of the speakers have talked about, end up rebreathing or reproducing the past, and not only reproducing the past, but even amplifying existing biases. Predictive policing has provided some very nice examples of where when you actually put the statistics of the existing inequality into the system, you can end up with a dynamical system that amplifies the effects that were in that bias in the first place over time and makes them extreme. So, machine learning fairness is, as has been said, a very active area of research. There are impossibility theorems, which you mentioned. You talked about it as a choice between different forms of fairness. A maybe more pessimistic way of putting it is the impossibility of simultaneously meeting the requirements, different kinds of requirements of fairness. So there is no answer. There is no way to do this that is perfect. There's no sense in which we can define an ultimate or perfect form of fairness mathematically. It's first and foremost a sociological problem or techno-sociological problem. And to be honest, my own approach has evolved in the last few years that we've been working on these kinds of problems to one in which I think less about all of the possible things that could go wrong with the system, because one will go crazy trying to think about all of those. And one thinks more about, given a particular system, what are the most problematic, obvious things that can go wrong, and how can we push back against them? There are, in any system, if one uses one's imagination, particular and historically contingent problems that arise through the use of that AI, that you can then do very specific sorts of interventions to push back against. But you have to be, in my opinion, necessarily targeted about how you approach those, and not think about them as isolated in some way from the environment, from the sociological environment in which they're going to operate. They're not principles that fall from the sky. They always have to apply in the particular scenario and the situation in which that system is being deployed. So a very active area of research. I could say much more about it, but I'd like to shift to another topic now. So the difference between Frank Rosenblatt in 1959 and now has partly to do with the scale of computation. Large-scale computing is what has allowed deep learning to happen and did not allow it to happen before. But another thing that allows deep learning to happen that made it impossible before was the availability of very large amounts of data to train these things. Our methods for training machine learning models today are extraordinarily inefficient compared with the way biological brains do the job. Our brains somehow manage in the first year of life, you're born a baby seemingly not knowing very much. Seemingly, there's an asterisk there, obviously. But in a year of mostly napping, you know how to walk and talk and understand things and perceive the world around you and make all sorts of sophisticated judgments. And the amount of information that you've been exposed to over that first year is minuscule compared with what is required to train a system with a similar number of parameters today using deep learning type techniques. That's also a very active area of research. But for the moment, we're stuck with systems that, even though in principle they can achieve superhuman performance, can only do so with superhuman amounts of training data to learn from. So given that framing, it's maybe no surprise that companies like Google have been at the forefront of development in AI. It's not only because we've brought very talented people together, but also because the era of online services is also the era in which it's been possible to accumulate enough training data to train these things. We do our best to make a lot of training sets available for academic researchers and so on, but it also is a fact that without online services, the training data to do a lot of these kinds of things would not have been possible to gather. So, with more compute and with more data, we've now gone to a very different spot. I joined Google right about at the beginning of this plot. There's no y-axis on it because Google doesn't want me to tell you how many projects they're doing. But suffice to say that the number of projects at Google that use deep learning in one form or another has absolutely exploded in the last 5 years. It touches every product and every service that the company makes, and I think a very similar plot could be shown for most other companies, and actually for a lot of academic institutions as well. So on the computing side of things, these are the kind of most famous pictures that might illustrate how big computing and deep learning go together. This is a TensorFlow processing unit pod in Google's data center. It can evaluate more than 100 petaflops, or gazillion operations per second. That's probably roughly about the same as a human brain. It's using quite a few more watts than the human brain does, I'm sorry to say. But this kind of development of specialized silicon in order to do deep learning in the data center has certainly been important in terms of our ability to scale up training of deep learning systems, especially. But what actually excites me even more than these TPU pods are, one more please, thank you, are these. So this is the Edge TPU, which you can see here on a 1 cent coin. I actually didn't know that the American 1 cent coin looks like that. I guess it's been a while since I've used one. But that shows you how small one of these chips is, the front and the back. Those things can do trillions of operations per second for less than a watt of power. And the reason that excites me so much is that I think that the future of machine learning and deep learning in particular extends far beyond data centers and is really about augmenting humanity in a variety of ways. It's almost as if these chips allow you to have a kind of exocortex or a part of your brain that is physically on your person. And I think that for a variety of reasons, including perhaps most importantly privacy, there are a lot of different applications in which you want the evaluation of these deep networks to be done entirely locally and without any other party in the picture. I could give many examples, but just to give you one, we released a feature a couple of years ago called Now Playing that involves allowing the phone to recognize all the music playing in the environment, so it shows it on the lock screen. I mean, it's nice if the lock screen shows you the music playing when it's coming from inside the phone. Why shouldn't it show it when it's coming from outside the phone as well in the coffee shop or something? It's a nice little feature. It's obvious that could not be done in the data center because that would mean that the phone would have to be sending the audio environment up to a data center continuously all the time. And that would be, in my opinion, an ethical violation as well as a violation of many laws in many countries, as well as technologically challenging, to say the least, because it costs a lot of power to send all of that data out. And it would be like every phone simultaneously being in a phone call at all times, which until 5G is completely ubiquitous will be impossible. So So that sort of exposes, I think, some of the reasons that I think that having local processing for doing inference is important. We're shipping more and more different kinds of features in phones and other kinds of devices that use this kind of local AI. But this raises the very important question of, if one is deploying neural nets that run in the personal environment, how on earth one trains them? Because in the web services context, the use of those neural nets generates the training data that allows you to test and to improve those models over time. If we are doing privacy-preserving AI that runs locally on devices, then there's no data coming back to Google or any other company that lets those models be improved. So the answer, I think, is a technique that we began developing a few years ago called Federated Learning. And this relies on the observation that even when we train neural net models today in the data center, that's actually a highly distributed and parallel process. The way it works is that the training data is divided up into batches. Each of those batches is sent to a different computer in the data center, and each of those computers calculates a local change in the neural net that would be required in order to make it perform better on its batch. Those changes are all sent to a parameter server, which adds up all of the changes and sends the sum back down. And in that cycle of local evaluations and summing, that's what I've just described is essentially an algorithm called stochastic gradient descent, which is the way almost all deep learning happens nowadays. So the idea behind federated learning is very simple. It's just, can we imagine that rather than that operation being distributed across many computers in the data center, it's distributed across all of our devices. In effect, doing something like turning all of our devices into a giant distributed worldwide supercomputer. The data that these things are trained on never leaves the device, and so remains entirely private to you. I find this idea very exciting because it really breaks the trade-off that has historically existed between deep learning, which is highly effective on the one hand, but also requires that those data be shared with a company, and on the other hand, privacy, which requires that companies, governments, et cetera, not see those data. So this is a way of scaling up deep learning to volumes of data that would actually be impossible to gather in any data center. I've sometimes talked about it as the dark matter of big data, in the sense that it's orders of magnitude bigger than any data that could ever arrive at any data center, and yet it's invisible. So, the metaphors, finding good metaphors for describing these techniques is actually one of the biggest challenges, because especially when we want to talk to policymakers about this kind of stuff, it's a complicated story, especially when I throw in things like homomorphic encryption, because you want to make sure that the updates that are happening on all those devices can't be used to reconstruct the training data on individual devices, and the way that that's done is by compressing and encrypting the changes on all of those devices and doing the additions all in the encrypted domain, so that only when hundreds or thousands have been added together does the answer pop out in plain text to get sent back down to all of the devices to be summed. So that means that the protections on privacy are really quite strong. It also means the story is quite complex. That's one of the reasons that we made this comic book, which I think the URL is up there, federated.withgoogle.com, to try and explain this in an engaging way with a little bit of a story behind it. So in summary, we developed this, I think, starting in 2015 or even earlier. We started publishing papers on the techniques in 2016, 2017. And we really began to talk about it much more in public at the last Google I/O a couple of months ago. And it's really turned into a whole burgeoning field. There's now a paper being published every day, more than one paper being published every day in this subfield of deep learning and federated learning, which is very exciting to see. We have deployed this on more than a billion smartphones already. It's powering the Google keyboard. So Google keyboard has actually quite a bit of AI in it in order to accelerate typing. And it's powering a few other features as well. I see those as early steps toward Google becoming essentially not just a giant robot in the cloud, but also a manufacturer of robots, if you want to think about it that way. I don't mean the kinds of robots that scurry around like R2-D2, but rather, I mean personal AIs that are inherently a part of you as opposed to a part of something else that is in your pocket or your purse all the time. So I really believe in that sort of picture of augmentation of humans using AI, and I think that these techniques of edge computing and federated learning are fundamental ways to bring the promises of deep learning into our lives with that augmentative premise. I think I'll end there, and do we have one more talk, or is it final time? Okay. Thank you all so much.